about ready to begin now. Welcome to the second in our series of Bay Area Computer History Perspectives talks, arranged by myself, Peter Nergsy, and Jeannie Trico, also from Sun Microsystems. And we both happen to have an interest in history. We had a speaker, Harry Husky, come from Santa Cruz last December to Sun to talk about his work in the pioneering days of computing. He worked on ENIAC at the University of Pennsylvania. He also worked for Alan Turing. Alan Turing was his boss for a year in England. And he went on to build the first computer in California, the SWAC, from National Bureau of Standards in LA. We had a lot to say, and there's a lot of interest here at Sun, which sparked the idea, but that's a series of talks, public talks on computer history. And we had the first in this series a month ago at Xerox PARC, and I think some of you here who were there at Xerox PARC. It was on computing at Livermore in 1963. 1963 was a transition year in computing at Livermore from the IBM era to the controlled data era. And we had John Ranaletti from Livermore who told us that he added up the total core memory of all the systems in use at Livermore in 1963, and the total core memory came out to 2 megabytes. That was the grand total of what they had to use there. We had a user there, Chuck Life, who told us that when he wanted to do a difficult and important program, he used assembly language. When he had something small, easy, they didn't care much about, he used Fortran. That was the days of computing in 1963. And I also want to, as well mentioning that program, I'd like to mention our next program. We'll take the summer off, Jeannie and I, but in September 28th, we'll have a program on IRMA. And IRMA was probably, I believe, the first major Bay Area contribution to the history of computing. The IRMA project started between Bank of America and Stanford Research Institute back in 1950.
Do you know who the spokesman was on the film about IRMA?
Oh, yes. Yeah. I just saw the Bank of America has a neat exhibit in Concord at their technical center. And they have video, and they have the IRMA press conference when Ronald Reagan was the spokesman. IRMA was developed by Bank of America and SRI for processing checks, and then General Electric took over the production development of IRMA, and Ronald Reagan was the spokesman at the time. I have here, I went to the IRMA exhibit last Friday, and I copied down a message from IRMA, IRMA's final farewell message. A message to all my co-workers from IRMA. In my 11 years of service to the Bank of America, I have been privileged to work with some of the bank's finest employees, from people like Emmett Jenkins, Dick Davis, John Coombs, and many more who were with me from the beginning, to Bob Lee and all of my current co-workers who are assisting me in the processing of traveler's checks, my final application. I can only say thank you. Together we have made great strides in banking. And I cannot help but feel, as the first computer system to be used for banking applications, that my retirement brings to close an historic era. To be the first in something is a great achievement, and I am very proud. But my success could not have been possible without the help of so many fine people. Although the end of an era is near and we will soon part, I will never forget my friends, and I wish you all the greatest success in the future. To my current and final assistants, I bid farewell, my best to all, IRMA. And that was IRMA's last words. So we'll hear more about IRMA on September 28th. Bank of America and also Stanford Research Institute. And now I'd like to introduce the speakers for our program tonight. As many of you know from the announcement, Saturday, May 22nd, was the 20th birthday of Ethernet. And we have here Bob Metcalfe, who 20 years ago wrote the memo that first mentioned Ethernet, David Boggs. Also John Shoch here at the end, and Ron Crane at the other end. I've asked John to be sort of the moderator for the program tonight, but they've been talking together, these guys, and they may do it differently, whatever they like. Sorry?
Thank you very much. Can everybody hear us if we just talk from here without the PA system? Does that work? I think that'll be okay. You guys can hear in the back? Great, thanks a lot. We've brought a lot of paraphernalia and a lot of things to talk about, but on the other hand, we haven't structured this very much. And I guess what we might do, Bob, is to follow up your suggestion, which do you want to describe what we want to do first?
Why did you come here? What questions would you like answered about the history of Ethernet?
Why does the transceiver weigh so much?
Why don't we collect some of the range of questions?
Other questions? Why did you come here?
Why did the cable always fall?
Excuse me?
Why did you choose 2.94?
Yes?
Why does the cable fall off?
Slide lock. The cable? No, slide locks.
Slide lock.
I'll take that one.
Other questions?
Did you ever think you'd be responsible for all of our careers?
You can pay us on the way out.
Yes, sir.
Where will we go now that one box can send 10 megabits in a second? Related to that, are you aware of the heavy sender capture problem?
The what?
Sounds like a thesis topic for me.
What do you think of FDI?
Now, wait a minute.
Well,
Some
that's
of
a
these
little bit
questions
off.
are about the future and about current events. We may not be qualified.
Go ahead.
What was your vision of applications at that time that you can remember?
Yeah.
I've never taught the band to play.
How what?
How costly were
How did this change your life in the park?
There's a collision.
We had a collision. I actually captured his transmission, but so you go ahead.
Ethernet is one of the few things that has lasted for 20 years. Generation years.
Why is it ASU.3 doesn't work with the wonderful specification?
IBM.
How can we ever let the 802.x people get away with redefining Ethernet types? And that's the biggest of that.
We'll talk about
Now,
that.
was that a question or a comment?
Well, coming off of the list here, it says, how did Ethernet become a standard? But then it follows on with what were the compromises, or were there any? I guess the answer is yes. Hearing those might be interesting.
More general two questions. Looking back at the standards issues, just commenting on standards and how you related to it as R&D going into standards, and what did you expect the useful life of Ethernet to be?
Who had the big money then to decide Ethernet?
Okay.
Why do you think you succeeded where idea of token rings failed?
You know, a lot of these questions have a premise to them, which we do not accept.
Ethernet has certain decisions it makes which involve more mechanism than the original ALOHA. And having you discuss why you added what you added and why you did things differently would be interesting.
We're going to huddle here for a moment.
Should we do a little bit of sort of background on the context of, talk a little bit about some of these stuff? That's a good question. And then do a little more about the Ethernet itself, sort of, and then roll all the way through the standard process. And sort of take it as a flow from there. Yeah. I mean, started.
Okay.
I mean, I've got some.
Why don't you call it Ethernet?
Okay, we have a plan. Here we go. Here we go. By the way, I brought with me the book I'm working on the history of Ethernet, and I'll be reading from it during the course of the next hour. The history of Ethernet, I think, can be divided into three phases. The first one is the one in which, and this is only approximate and there's a lot of details left out, but in the first phase, the technology was invented by David and me. The technology. And in the second phase, the idea of a standard was invented by Gordon Bell, who's here. Gordon, raise your hand. That idea was invented in a meeting in February 1979. That is, that Ethernet should be a standard. In a meeting between the two of us, and we can't remember, or at least the last time I talked to Gordon, he could not remember who actually had the idea. It was the idea that Ethernet ought to be a standard, the second invention. And the third invention, by my accounts, and by the way, you may detect some disagreement among the three of us. I hope you're listening for that. The third invention was the invention of the hot product, circa 1982, which Ron Crane and I were involved in at 3Com Corporation. So the history, the technology, the standard, the hot product. So now going back to that first question about phase one, the invention of the technology was in circa 1973. The memo inventing Ethernet was written on an IBM correcting selectric typewriter. There was online word processing at that time using a 2741 at dialing up at 150 bits per second to a time-sharing machine somewhere. You could do word processing, but rather than get into all that, I typed it on a selectric typewriter using the orator ball so that it would be legible from the back.
And then he decorated it with felt tip pens, which is also part of his style. In fact, the word ether is written in large felt tip marking right here. That's what it comes from.
So
That's,
ether.
That's what makes this the memo that we declare to be the one that marks the birthday.
The word ether had been floating around the Xerox Research Center, as I recall, and the ether comes from physics. Do you all know that? Ether, the word ether is and it was thought to be
The luminiferous ether that pervaded the universe and that light moved through the way sound moved through air.
And Michelson and Morley proved there was no ether, so that term was up for grabs, and we grabbed it.
While we're here, we might as well. Well.
I don't like it.
The first two altos that. No, I'll wait.
They all know how to stop at one.
The Ethernet project was issued two of the first altos. Altos were very scarce at the time, and we named them Michelson and Morley. Michelson was Alto 101, the first one basically, and Morley we got a few months or a month or so later. It was Alto number 110. So we named them after the guys who proved that the ether didn't exist.
Bob, do you want to say a little bit about sort of what the competing alternative suggested design was? Because that was sort of the backdrop for the ideas and the relationship to the ALOHAnet and the ARPANET. Friends with Bobby, no different approach.
MCA.
Okay, Bob, talk about these things? Okay. Upon arriving at the Xerox Research Center in July of '72, I had been working on the ARPA computer network, which connected mini computers at 50 kilobits per second across the country. At Xerox Palo Alto Research Center, there were Nova 800s, which were 16-bit mini computers interconnected by a 16-bit parallel big thick cable that could connect up to 15 of them at distances, at short distances, hundreds of feet maybe if you were lucky. In fact, we had slowed, not me, had slowed it down so it could go a little bit further. And we had two of them, so we had 29 Novas on these two big cables. Why 29? Because one of them was on both of these cables, so it was 15 and 15, and one of them was on both, hence 29, and it had to be really slowed down to half speed to work. And then we said, let's do a new network for this new personal computer that was being built called the Alto, and the best idea around was that of Charles Simonyi, who's currently at Microsoft, was to build ARPANET-like imps, micro imps, that would, instead of running at 50 kilobits per second, would run at 50 megabits per second. And we began designing, Charles and I began working together because I was the networking guy, building these little micro imps. And then Charles got taken away from the project to write a bitmap editor called Bravo. It had a mouse on it, and it had a big monitor like this. So Charles went off to do that, leaving me unsupervised. And I had done part of my PhD work on the Aloha network and dropped the microcomputer, the micro imp idea for the Ethernet, the Alto Aloha network idea, because it just seems simpler. And who wants to go at 50 megabits per second anyway? Okay, we're next.
Let's see, I guess I'll say how I met you. I was working part-time at Xerox at the time. I was a grad student at Stanford. I was a grad student at Stanford in the double E department, working on my master's degree and intending to go get my PhD. And I was working, I heard Alan Kay, yeah, right. Alan Kay came and gave the EE380 seminar talk, which is every Friday at about 4:15 in the afternoon. They invite people from industry to come and give a talk about what they're doing. And all of the master's students, I think, are pretty much required to attend that seminar. So I attended it, and Alan was talking, and he was describing how another group at PARC was designing and building a machine that could be microprogrammed to be a PDP-10. And I thought that was pretty neat because I was into high-performance computer design at the time. So I stayed afterwards and needled him and tried to get a summer job at PARC. But I didn't really fit in with the learning research group, which was small talk and language design and stuff like that. But there was another group at Xerox building office systems, not Bob's group, building centralized multi-computer office systems. And they needed the kind of background that I had. I had some background in television and communications. So I started working with them. And the first thing I did was assemble Nova computer systems. We were getting them at the rate of about one a week. And so they'd come in big crates, and I'd take them apart and bolt them into racks and configure them, test them out, roll them down the hall, and give them to the software guys who were developing the multi-processor operating system for it. Bob had designed a ARPANET interface for the Nova computer to plug into the PDP-10 that was being built. And the other group also wanted an ARPANET interface for their multi-processor office system. So they asked him to make another copy of that ARPANET interface. And so he asked the laboratory staff to do that, and they did. And then he had to debug it somewhere, and he needed a Nova to plug it into and debug it. So I was assembling Novas, and I had a test stand Nova just sitting there, and it was guaranteed to work. So he asked if he could use my Nova, and of course I got sucked into helping him debug it. I guess actually I'd seen him a little bit before. At the time he had a beard, and this guy showed up in the basement of Building 34 with a 1,000-foot spool of coax cable and set it down on a workbench, and he got out a soldering iron, and he had an oscilloscope and a pulse generator, and was soldering resistors on the end of the coax and hitting it with a pulse generator and looking at it with a scope. And I was in the other part of the room assembling Novas at the time and sort of watching the guy and wondering what he was doing. I found out a little later when he asked me to help him with the ARPANET interface.
So there I was with the soldering iron, and I would burn my finger on the soldering iron because I'm not very good with a soldering iron. And this guy is very good with a soldering iron. Could you help me with this? So I'm putting this connector here on the end of this coax. Would you help me with this? And before I knew it, he was doing all the soldering on the thing.
That's actually the end of my story. Well, I guess to finish it, Bob at the time was writing. Bob had arrived from MIT a few months before. He beat me to PARC by, I don't know, maybe 6 months. You said July of 72? I think I arrived in March of 73, something like that, March or April.
Newcomer.
Like you all be.
Oh, right, yeah. You were hired as a file cabinet, weren't you?
Right.
They had a payment problem, and each time he needed to be paid, they had to buy a file
There
cabinet.
was a hiring freeze, and so sort of, you got hired as a contractor or a piece of capital equipment or whatever.
Anyway, Bob was toiling away writing all the memos that we're referring to here. I didn't know who he was at the time. He was working on the Alto ALOHANet. He had, of course, analyzed the ALOHANet and extended its mathematical analysis in his PhD dissertation at MIT. So that's one reason why he was sort of thinking along these lines. Anyway, when it came time to start applying a soldering iron and building some of his ideas, he needed a collaborator, and so he knew me, and I can remember in about April or May of '73, April I think, he and I went over to my supervisor, Bill English, who by the way used to work at SRI and worked with Doug Engelbart, and I think Bill is credited as one of the major contributors to the original mouse. Yeah, okay, his name's on the patent. Anyway, so I was working for Bill English at the time, and Bob and I came to Bill English's office, and Bob asked if he could borrow me for a couple of months, and Bill never got any work out of me again.
So let me read you the first few lines of the Ethernet memo on May 22nd, 1973. It's to the Alto Aloha distribution from me, subject Ether acquisition. Here is more rough stuff on the Alto Aloha network. I propose we stop calling this thing the Alto Aloha network. First, because it should support any number of different kinds of stations, say Nova or PDP-11 ... Second, because the organization is beginning to look very much more beautiful than the Aloha radio network. To use Charles's, quote, beautiful.
Charles Simone.
Maybe the Ether network. Suggestion? I hope to be simulating soon. Help inputs? I hope you will not be offended by my attempts to make this thinking and design appear theoretical. And then it goes on. Are we done with phase one of the invention of Ethernet or not?
On this memo, you've written in a couple of other names other than Ethernet. You suggested Lazy Susan or Bulletin Board or Parley or Parliamentary Procedure. Ethernet stuck. Okay, what's next? Yeah.
One thing I remember as being a problem is the MCA was supposed to be error-free, and
Oh, yeah.
it wasn't, and we had a lot of trouble with that. The nicest thing about the Ethernet was that it was an unreliable network.
That comes right out of Bob's thesis. I think you close a chapter by saying everyone should treat everything, whether it's local or remote, as if it's remote and expect the worst, and then be surprised pleasantly when it works well. And as opposed to the other approach, which is to assume everything is going to work correctly, and then when it doesn't, nothing works at all. The original ARPANET control protocols assumed that the ARPANET always worked. That is, they believed the guys who built the network who said, you give us a packet, we will deliver it to its final destination, or we will tell you it didn't get there. And so everyone wrote the original ARPANET control protocols assuming that was so. And it wasn't. And every time they lost a packet, be it once a day, everything locked up. And then they went back and they did it all over again. And they sort of assumed that maybe packets could maybe get lost, but they weren't really sure about it. And things started to get stable at that point.
So, summarizing, David and I then spent 2 years together, working until we got tired, and then going to sleep, and then sleeping until we woke up, and then waking up. And we found that our days precessed around the clock. And the only awkwardness was that every Tuesday we had a meeting at 1 or 12 o'clock or 1 in the afternoon, a meeting called Dealer. And that was really awkward because often on Tuesday we would be out of phase with that meeting. And we built this Ethernet cards that plugged into the Alto, and they ran at 2.94 megabits per second because of the following disgusting design decision that we made. We were trying to squeeze all the electronics onto a board very similar, if not exactly like the one David has just picked up, and it wouldn't fit. And we had a clock on the board, or we thought at one time we would have a clock to clock the data out onto the network. And one of the optimizations we made was to take the system clock of the Alto, which clocked every 170 nanoseconds, and use that to drive the phase decoder and encoder on the card. And if you do the arithmetic, 170 nanoseconds Manchester encoded divided by 2 results in 2.94 megabits per second. And I was always reluctant to round it up to 3. Most people think it was 3. And the reason I was reluctant is that the round-off error was bigger than the fastest circuits in the ARPA network, which were 50 kilobits per second. And I was reluctant to just exaggerate by 50 kilobits per second.
This is one of the very early Alto Ethernet boards. This gives you an idea of the size of a logic board in an Alto. I think it had about 84 parts, 84 chips on it. We built
when chips were chips.
little things like 2 flip-flops per chip or 4 NAND gates. The very first Ethernet board was built on a wire wrap, ALGAT wire wrap card that held 60 ICs. And it was, that particular interface was full duplex. That is, it had a completely separate transmitter and receiver data path, 2 separate FIFOs. And then the Alto happened to be a multiprocessor at a low level, and it actually used 2 hardware processes, one for transmit and one for receive. For various reasons, we abandoned that design. Designs are like waffles. You should throw the first few away anyway. So we threw that one away. I've got a small picture of it down there. I don't have it anymore. Last September, I gave it along with the original lab notebooks to the Smithsonian. They also have a couple of Altos in their collection, and they were delighted to have the original Ethernet. I also gave them the original, one of the 2 original transceivers that Tat Lam built for us. We'll get to talk about Tat Lam in a moment. But anyway, so we built one wire wrap board. Actually, we designed the Alto wire wrap board. And while we were waiting for it to be fabbed, we designed a Nova board, a quick and dirty Nova design. And then the Alto design came back, and we debugged the Alto design, and then we debugged the Nova design. So we built this one Alto design, threw it away, designed another version of that, made 10 wire wrap versions of that while waiting for the production process on the PC board. So we had, at one point, we had about 20 or 30 Altos, but we only had 10 Ethernet interfaces. Then the PC board started to flow in, and we quickly caught up with production. So this one that doesn't have any solder mask on it is one of the first 5 protos of the first PC board version of an Ethernet. It's, in the scheme of things, it would be about Ethernet interface number somewhere between 15 and 20 altogether.
Was the protocol implemented on the host at that time, or some?
What protocol do you mean?
The
You mean
Ethernet?
back off and that stuff?
Yeah.
No, it was done in microcode. The Alto was microcoded. So what's in hardware here is just the hardware main loop. The address recognition, binary exponential back off, and the DMA address and word count counters for moving data back and forth. Those were just registers and variables in the Alto microprogram. One of the things we did when we threw away the first design was go down to 1 hardware process. And so the second version of the board was half duplex. And that actually caused infinite problems for years after that. And I swore I'd never, ever do another half duplex Ethernet interface. And I never have.
Me neither. No, that's wrong, actually. Didn't we do one? Wasn't the Etherlink half duplex?
It was half duplex. The controller was not, the Ethernet controller on the Etherlink, this was the one of the early cards for the IBM PC bus at 3Com. It used a controller chip which was full duplex, but the bus interface was half duplex. That is, we could either be sending or receiving a packet, but we couldn't be sending a packet and actually transferring data on the PC bus at the same time. Yes, as Pitts points out, we had only 1 packet buffer. That was the primary reason for this.
SRAM or whatever was expensive.
Real estate was really the big problem. There wasn't any space left after we put the encoder, decoder, transceiver, Ethernet controller, and bus interface onto the board.
John, what about the software in those early Ethernets?
Oh, talk about the Nova software situation.
Well, one of the just to fill in some of the background, I had actually been at Xerox. I hired in a somewhat similar way. I had taken a class from Alan Kay at Stanford, and at the end of it, he asked me if I wanted to, through a funny set of circumstances, whether I wanted a summer job, and it turned into 14 years, but sort of in a series of 6-month wind sprints. And I came in the early days when we had, I guess the very first, this was in the spring of '71, and we were just working on Macs, which was the time sharing machines. There were a couple Novas. There wasn't a lot around. There were some TI terminals that cost about as much as a car. If you remember.
Silent 700.
Silent 700, which was an arm stretch, a portable, a little less portable than an Osborne. And at the time, it cost about the same as a VW Bug, was one of the things that I observed. And so I worked on a bunch of things, including what became Smalltalk in the Learn and Research Group. And we were developing Smalltalk initially with a version of it on the Nova and later an implementation on the Alto. And some of you may know Dan Ingalls, who was at Apple for a while, worked on a lot of that. Larry Tesler and others pitched in. And along the way, we were doing programming on a prototype system, the Research Character Generator, which had a bitmap graphics system that allowed us to do some of the earliest bitmap graphics and mouse control and some early Smalltalk implementations. And I was doing some software for Smalltalk and sort of watching this whole project. And one of my clearest recollections and sort of watching the evolution of the Ethernet, and there was a point where it's, okay, we need to really try to do something with this, and we need a little protocol to move some files around, to actually connect the machines together. And as I recall, I think I was going to do the one, Bob was going to do one in Mesa. We were going to design a little protocol. You don't remember this? Mesa. You were learning Mesa.
MPL, this is way too early. BCPL.
No, I did the one in BCPL for the Nova. Maybe MPL. Maybe you're right. You were going to do one of them. I don't remember which. And I did it for the in assembly language for the Nova, and was going to do it in Smalltalk to run on the Alto. Now, the mismatch in performance of these environments is probably at least 2 decimal orders of magnitude because Smalltalk was an interpreted system at the time. And one of my clearest recollections, and Bob is a little more, to this day, a little more structured and organized than I am, and we sat down and we'd sketched out this very simple file transfer program we were going to do, which later became known as the EEFTP, Experimental Ethernet File Transfer Protocol. It was not an internet protocol, specific packets on the Ethernet with packet types. And Bob had very careful notes, as he does to this day. You recall this event? And and he had a lab notebook, which those who were more organized than I was had a real honest to God lab notebook with page numbers and dates, and you'd sort of pay real attention to it. And he had this bound spiral lab notebook. And we sat down at the round table in your office, and in about 5 minutes sort of sketched out, well, we're going to do this little simple act per packet, here comes some data, here's a request for a connection, here comes some data, act the data, and so on, and just a very simple, it took about a page to sketch out the formats of the packet and a few type codes or something, and this was sort of something that we had brewed up, or I think you had brewed up, and you were in the midst of implementing it or whatever, and I was going to go implement it in Smalltalk. And Bob had written all this very carefully in his lab notebook with the numbered page and the date and everything else, and not fully appreciating the symbolism of this. I said, oh yeah, okay, I'll go do that. And I reached over and ripped the page out of the lab notebook. Right. And to this day, I wish I had the film of the look on Bob's face when I had wounded him by ripping from his soul a piece of his lab notebook, which I learned not to do again. And we merrily went off, and I implemented an assembly language version on the Data General Nova, and a little version in Smalltalk, which was an interpreted language and really easy to implement, and you sort of didn't really want to have to focus on performance. But that was the origin of what was originally called the EEFTP, Experimental Ethernet File Transfer Protocol, which was a very simple act per packet kind of thing, which actually worked quite well.
Saved our butt once during the disk cataclysm.
Oh, tell the story.
The disk cataclysm. The disk controller for the Alto was designed by Ed McCrite, who now works at Adobe. Yeah, right. And he got a little bit too aggressive on packing the bits into the disk, and the disk wasn't all that reliable. So after a while, he backed off, and he was going to change the crystal in the disk controller, thereby spacing the bits out a little more. But that meant that all old disks would become unreadable. So we converted an Alto. I guess we must have had a couple with Ethernets by then. There must be, one of them was certainly the original design controller we threw away later, and the other one must have been a later controller. But anyway, we had one Alto the old way and one Alto the new way, and people lined up and plugged their disk in and copied the files they really needed from the old format to the new format, and then we converted all the disks over. And that's the first time I think the lab actually got any much real use out of the Ethernet. And it was using their EFTP stuff.
So let me describe how the EFTP worked. The protocol did not know about file names, which is sort of awkward for a file transfer protocol. So you'd go up to the Alto, which was going to either the server, and you would type EEFTP/S, something like that. And it would come up and go Z, 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 forever. Then you go to the other machine, which would be, I guess you'd call it the client. And then you'd say EFTP, and then you'd give the address, an 8-bit number. I guess, I forget whether it was octal or whatever, decimal. And then a file name. Oh, I forgot to mention you had to give a file name the first time. File name. EFTP file name /S, meaning I'm the server. If you get a file, put it under this name. You go to the other machine and you type EEFTP, send it to this machine, it being this file, and then it would go bang, 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 end. The bangs were the individual bang is an exclamation point. I'm sorry. Everyone knows bang is exclamation point. And so each bang was a packet. And so you'd watch them go bang, 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 bang at very high speed, 3 million bits per second, bang, 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 right across the network. And that was the EEFTP. And it was a sort of simplified version of the ARPANET EFTP, basically stripping out all that unnecessary stuff like file names.
Right. It also became a section in the Ethernet paper that we published in CACM in 75 or 6.
July 76.
Right. Oh, I see you remember.
Yeah, I've got it right here.
Shall we talk about transceivers a little bit here? Because that was pretty major.
Let's do transceivers, then we have to move on and talk about the standardization part.
Okay, all right.
Question before you get on to the standardization. You started off with this big parallel cable, which would only be a local area net. And you've talked about the ALOHAnet, which was really a wide area net as well. And you called Ethernet a local area net, but it sounds like you really had in mind wide area networking when you started.
No, we had in mind 1 mile in diameter, 1 megabit per second, and 100 hosts. And when we finally realized it came out to a mile or a kilometer. We were a little vague on that. 3 megabits per second and 256 hosts. And we always said a building or a campus of closely spaced buildings.
Did you ever consider a parallel type of transmission, 8 bits wide or
Chuck Thacker did X.
Yeah, we did consider parallel, and we eliminated it because if you have 16 cables, it's tough. And then you have 16 drivers and 16 receivers, and the connectors have to be 16 of everything. So if you're going to go any distance at all, we reasoned, like a mile or a kilometer if things didn't work out well, then you would it was much better to go serial. I think the decision was fundamental that to go as far as around a building, you really needed to go serial, and parallel was a dead end at that range.
So an MCA connector, you'd understand.
It was a 50-pin DE series, giant, or not, whatever it was, DD series, giant connector. And the cable was enormous, and the strain relief would always be pulling one of the wires out because the bus would go down.
So it was that bad experience that
today this fuzzy plug is about half the size of the disc.
Yeah.
Got it.
Right. Yes.
Okay. Let's talk a little.
There was a spec called the X-wire spec. How did the X-wire spec differ than the original Ethernet version 1 when the Office Products Division was attempting to standardize X-wire? Was that Thacker's design?
Can we hold that for a moment? We'll talk about that with standardization. I just want to say a little bit about transceivers because they're so important. I built a couple of early transceivers. Yeah, that's a transceiver. Actually, I'm going to show a couple of others. Yeah, I built a bunch of old transceivers by taking coax line drivers out of IC catalogs and doing that. But I'm not really an analog circuit designer, and I knew I was way out of my depth. But it was good enough for hooking together 2 hosts over a piece of coax, but it wouldn't really work with 3, and I never really did collision detection very well. So we were thrashing around looking for help, and we found Bob St. John here helped us for a while. He sketched out an early transceiver design. He got called away on, he was actually working for another group, and they insisted that he go and do what they hired him to do. So So we never followed up on his transceiver design. But we did find a guy named Tat Lam, who was a contract analog circuit designer, designing high-speed video stuff for one of the groups that was building office systems and needed to display crisp letters on large CRTs, and so he was doing that. And we asked him to take a stab at the transceiver design. And so he said he would. So we wrote him a contract for the best darn contracts we ever wrote for $2,000. He went away and designed basically the working Ethernet transceiver, which we used for years afterwards. So he came back about a month later with with initially one breadboard that had sheet copper on one side and a big strip cut out of it, so that there were two halves, the ether half and the computer half, and everything going between them went through little pulse transformers because we were very concerned about safety back then. So he made two of these, and they worked beautifully, and so we said, great, we want some more. And we wrote another $2,000 contract, and a month later he came back with 10 completely packaged Ethernet transceivers with printed circuit boards and everything. Here's one of them. This is Ethernet transceiver number 106. So this is one of the first 10 built by Tat Lam. And notice also that this thing has a BNC connector on it, thin wire, in 1973. We knew what we were doing. Tat continued to develop that transceiver. He made thousands of them for us at Xerox. And then as soon as it became a 10 megabit spec, he of course was ready with his 10 megabit transceiver, which looks remarkably similar to the 3 megabit one. And he made quite a bit of money off of this. So Tat really saved us. If he hadn't come through and designed a working Ethernet transceiver, the Ethernet might have died right there. That's another good story. We were wondering how to tap into coax, or even what coax to use. At one point we tried triax, and we hired a wizard mechanical designer from Xerox in Los Angeles to design a clamp that would pierce the cable and give you access to all three conductors in it. And it actually works, and it's sort of what we ended up doing. But the guy in the office next to me at PARC, and about 4 offices around the corner from Bob, was David Liddell, later of Xerox vice president and now president or director or whatever of interval research. And in a previous life, David Liddell had installed cable TV systems in the Detroit public schools. And he knew exactly what we needed. He said, you need a Gerald Electronics Incorporated cable TV tap block. And he got us a catalog. And that's this. It's a metal casting you clamp around the cable, and then you, yeah, here's one. And then you screw in a tool which drills a core out of the side of the coax. And then, having prepared the hole, you screw in the transceiver, which has a little pin on the end called a stinger, and that makes the connection without having to cut the coax and disturb everyone else who's using the cable. So Liddell's the one who put us on the track for that.
Talk about the migration from the first generation to second generation through the X-wire, so on.
That's, I got to Xerox around June of 1977. So the environment upon my arrival had been prepared by these guys. They had working hardware and software and operating, and in fact it connected to laser printer in the building across the street. So when people wished to print their files, the network was actually in regular use.
What the protocol was that was embedded inside Bravo, the printers?
What?
EFTP.
EFTP was the protocol embedded in Bravo to send.
Bob wrote the code that received the files at the printer and spooled them on the disk. And it became the first laser printer. It was called EARS, for
Yes.
Internet Alto RCG Slot.
Right.
RG stands for Research Character Generator, and SLOT stands for Scanning Laser Output Terminal, which is the laser printhead.
Right. The laser printhead. Right. The laser printhead was basically a mechanism that was dropped into a Xerox 7000 engine and the light box removed from the printer. The project, my job when I got to Xerox was to figure out how to take this 3 megabit system to a higher speed, 10 or 20 megabits per second. So the first thing I did was start looking at what the signals looked like in the cable, trying to characterize how far we could go. And there were several limitations that we ran into. One of them was, and principally, was the reflections from the taps on the coax cable. The piercing taps had an electrical characteristic called capacitance, as well as shunt resistance, both of which were issues in the design of how many taps could be cascaded on the cable, and also, to some extent, how close you could put them together. So we looked at things, and there were several parameters that ultimately caused us to make some changes in the system, and mostly they were just refinements. Because of the reflection was proportional to the cable impedance, the tap capacitance, and the rise and fall times of the signal. So we controlled the rise fall times. The best you could do was a sine wave. The tap capacitance we drove down to a couple picofarads, and the cable impedance we moved from 75 ohm cable, which was typical in the cable TV industry, to 50 ohm cable, which was the other standard cable impedance. The goal was to use off-the-shelf stuff, not design a brand new cable. And we looked at various types of connectors. The old UHF series connectors was one, but those were actually 28 ohm impedance. So they looked like several picofarad lumps on the cable, just joining cable sections. So we moved to the N series connectors, which are the connectors you see on the fat coax cable today. And we used a cable that was the same as the RG8 foam type of cable, but and we used that inside of Xerox. As when we started working on the specification, there were issues of or concerns that RF signals from radio stations might create currents in the shield of the cable and thus have currents inside the cable. So we, at least for the first version of the Ethernet spec, had multiple shields in the cable. So it was probably one of the best shielded cables around at the time. That it had to be made special. Another issue in moving the speed from 3 megabits to 10 megabits was how much we could fit onto the controller board. We had a project that was called D0. This was a processor which had boards that were approximately 11 by 14 inches for our circuit boards. And we tried to fit all we could on there. We were building controllers. Two other people who I think are here right now, Roy Ogus and Bob Garner, designed the digital part of those controllers. And we had some limitations. For example, in the CRC circuitry, the fastest chip we could get would only run at 10 megabits a second. Otherwise, we had to do a discrete CRC calculation, and that consumed a lot more parts than we actually had space for on the board. Now that, along with the limitations in the coax system, caused us to basically migrate to the 10 megabit per second number to avoid the worst. It was in the coax system, it was based on a calculation of worst case reflections or standing waves in the coax cable. In the development of the transceiver for 10 megabits and in the quest for lower capacitance taps, we did a number of things. We started with the Gerald taps, which is a small assembly here. We worked with some companies. We tried making lower capacitance versions of these. And in the standardization effort, we worked with companies like AMP, which made molded assemblies, which you'd start out with a device like this. However, it required a tool, and they actually had a special tool which you had to put onto the cable with an Allen wrench. And then you had a small drill which you would use to drill out the stuff, and then you had
battery-operated drill to do it with, and carrying case.
They ultimately had a battery-operated drill. They had another flange mount version which used the same type of tools, and ultimately they went to the a small version, which is most what you see today, the amp or vampire tap, relatively small one. This one is still in production. These appeared on some transceivers from early manufacturers. This mechanism actually showed up on a transceiver from Digital Equipment Corporation after the standard came out. It was their H4000. It looks somewhat like Battlestar Galactica failing. So, and there's more things here which appeared. Let's see, the Xerox wire. I believe this is one of the.
That was developed by somebody in El Segundo, is what
this,
I was told.
Yes, this.
It's a souvenir.
This was one of the early transceivers in the project at Xerox to do that transition from the 3 megabit to the 10 megabit network. It was called Xerox Wire, and it kept that name until the beginning of the standards effort with DEC and Intel, and Bob will get into how we got to that in a moment. Internally, we had some specifications which we called the Xerox Wire spec. It basically had standardized on a 10 megabit transmission system. We had a 16-bit CRC, which would later move to 32 for the final Ethernet standard. And the signaling on the coax was basically like what we have today, except the polarity at that time was positive rather than negative polarity, which is what's used right now. And that was a compromise to allow the easy implementation and standard IC technology. Question?
Yeah, can you explain why there are stripes on the cable?
Why there are stripes, black stripes on the cable. In the calculations that we had done, there was a desire, and this was a result of the Ethernet standard when it was released, to limit the density of taps on the cable to a certain number. We put stripes on the cable to limit how close the transceivers would be placed to each other. There's a rule that says they should be placed at least 2.5 meters apart, and the rule actually said you have to put them on the stripes. In practice, all you have to do is just keep them some reasonable distance away from other taps, and that will reduce the likelihood that you'll get standing waves that would cause a problem in the cable system.
In practice, I have never ever put it. No. In fact, I've gone out of my way to never put a tap on a stripe.
Yes, I likewise have found that that's something that was in the spec, but was really not necessary. Yes.
Are splice taps any better or worse impedance-wise? Better characteristics?
You know, like type N connectors in a barrel? Yeah. They're about 10 times, 10 times worse than a vampire tap. Roughly.
The taps, basically what you're saying is connectorized taps. Those depend, you get reflections because of extra capacitance or because the cable is not the same impedance. So whenever you have a connectorized tap, your biggest source of reflection is most likely from the fact that you may have two different cables plugged together. That is, the cable could go from 48 ohms to 52 ohms, and you could get a couple % reflection from that point. The N-series connectors, if you were to cut the cable, install the connectors, and put a barrel on, will produce no reflection on a 50 ohm cable. But that's not true of the old UHF series connectors. Those were the old UHF series connectors looked like about 2 or 3 picofarads of capacitance at that point if you had a UHF barrel installed. Just as a note, if you were to remove the plastic dielectric from it, that raises the impedance up to around 50 ohms, so you don't get a reflection. But you have to be real careful putting it together because the center pin is supported by the plastic. So you have to put the pieces on separately.
Maybe just before we go to the standard stuff. Sorry, David.
Yeah.
Ron designed the transceiver that did have 2 end connectors on here, and then he carefully equalized the coax inside so that this thing looks pretty ideal and doesn't disturb the signal transmission much at all. It's about as good as you can do. But what I said before about a factor of 10 was the rule of thumb that I used on the 3 megabit Ethernet with UHF connectors and 75 ohm coax. A pressure tap was about 10 times as good in terms of signal reflection you see on a scope versus 2 UHF connectors and a barrel in between.
I was just going to add a couple things about the transition from the experimental Ethernet to what became known as the Ethernet. We'll talk about the standardization process. During this time period, we'd had a chance to run a bunch of software, and a guy named John Hupp and I had done some measurements on the Ethernet, and we were collecting a bunch of stuff about the behavior and performance of the system. And one of the lessons from this is that we had the good fortune to do the first generation system and then sort of do it all again in trying to do the standard product, which many people had their hand in. And we learned a lot from that, and one of the frustrations we had when we later got into standardization was there were a lot of people inventing things on the fly for the first system, and we knew about all the incredibly odd things we had learned from the first system which we would not have predicted. And there's just a couple random ones that come to mind. We had built, in looking at the packets, you'd sort of, and in particular we had some stuff that normally you keep the good packets and you throw the bad ones away. And so we'd run some stuff where you keep all the bad packets at a very low level and you throw all the good ones away, and then you'd stare at these things and you'd say, what the hell is this piece of garbage that got through? And you'd sort of eyeball it and say, I wonder what those bits are. And we looked at some, and lo and behold, we looked at one and we said, gee, this whole packet, it shifted 13 bits. We lost the first 13 bits. What happened here? And we wrote a program to sort of be able to shift packets around and try to figure out what had happened to them. And turned out the Manchester coding had not locked up properly because there was only a single bit on the front or something. And that led to some rethinking about, gee, maybe one bit isn't enough and we ought to put some more bits, and it ended up 32, 64 on the front end of the second generation system. So we sort of learned something from that. We learned a lot about performance, that the major cause of bad performance was not bad packets, it was having your receiver turned off. And that if you weren't listening, it was pretty hard to hear anything. And you had, so that if you had, in particular, if you had a system that was on a server and it was catching a packet and it was pretty slow to turn the receiver back on, you were guaranteed to miss every other packet and you wondered why your performance wasn't very good. And so that sort of got into the second generation system about, gee, you have to make sure you keep the receiver on or get it turned around quickly. And one of my favorites was the pathology, and I don't quite recall the sequence of the development, and we rewrite some of this as we tell the stories, but we had a particular pathology where some machine, the system was going down and Max was not behaving well and the network was sort of in a shambles, and we got a bunch of tools out and sort of ran some stuff to watch, and I think we had PUP packets at the time, and you'd look at this RFC, a request for a connection to Max, which was a major server. People were storing a lot of files there, and you'd watch and Max would send back, an okay, I'm ready to start, a response to the RFC, followed immediately by another packet that said, error, I can't do that. We sort of scratched our heads and said, boy, something is really screwed up here. And you'd watch it happen again, and it would send back a packet that said, no, I refuse to accept your connection, followed immediately by a packet that said, I accept your connection. And we sort of stared at it, and I've forgotten who, I think it was a group of us sort of, late one night looking at this thing. And we finally figured out that what had happened is there were two different machines that had the same ID number. And so a host was sitting there sending out a packet to Max to open a connection, and Max was saying, oh yeah, I'll open the connection, and this other machine, which happened to have the same 8-bit serial number, was very merrily sending back a packet that said, I don't know why you're asking to connect to me because I don't have that service, so go away. And not surprisingly, the client was a little confused by these two answers. And we sort of said, where the hell is this other machine, who thinks that he's Max and has picked up his 8-bit number, because we had the numbers were not unique, they were specific to the Ethernet. And as I recall, the fault was that someone had a machine in another building that had an 8-bit.
No, it was actually broken hardware. There was a machine on the third floor through a repeater, which made it hard to find. It was coming through a repeater. And the machine had a stuck bit in the data path, and it was turning its address into Max's address. And it wasn't affecting, it was flaky. It only seemed to hit the address fields or something like that.
Yeah. And it's the kind of thing, who could sit down and anticipate that this is going to be a problem? And again, as we get to the standardization, we had the good fortune to have used the experimental system. It's one of the reasons why we then went and said, gee, network relative host addresses are going to cause you a problem. A more general version of this is if you move a machine from one network to another, and it had an 8-bit network number, an 8-bit machine number on one network, and you put it somewhere else without any more identifying information, you were going to have this problem. This was sort of a big, oh shit, what are we going to do about this one? Yeah, and this would start to happen. And it's an example, and so the solution is you have a 32, everyone thought we were crazy, 32-bit identifiers for Ethernets. how are you ever going to have 2 to the 32nd devices on a single Ethernet? And we kept saying, you don't understand how strange this stuff can be. And going into the standardization process, we felt pretty good about all the time we'd spent learning about all that and trying to get it right. And there's lots of people, by the way, in this room. Dave was part of that, and others, who really helped resolve a lot of those things as we learned it. But, you might want to then lead into standardization.
We're having trouble cramming 20 years into an hour. Any advice on timing? We can't take a break. If we take a break, we're going home. Yes.
Before you get into the standards, you mentioned the strides and so forth. Would you just comment what, looking back, you feel you over-engineered?
At what stage?
Just looking back now, before you get into the standards discussion.
Well, all the over-engineering occurred during the standards.
Before you get into the standards, was there any over-engineering before you get to standards in your mind looking back?
I think the original experimental Ethernet was very much under-engineered. 8-bit addresses.
It was really bad. That got fixed.
It was done by computer scientists. Not.
I'll ask a question when you're finished with this, with the
Right.
standards section.
Yeah, David?
But you kept carrier sense, you kept collision detect, you kept exponential backoff, there's whatever the rest of the list is of major decisions, things that you kept, all of which constituted a collection of additions over the original Aloha that one might say made it dramatically more complicated. Would you care to talk about why it was important to have kept each of those or any of those?
18% throughput.
Yeah, the ALOHAnet was capable of 18% throughput, and the Ethernet is capable of 99.9999999% throughput, depending on packet size. And so all these, he referred to them as complications that were added to the Aloha network, like carrier sense, so you wouldn't clobber a packet that was already there, and collision detection, so that you would be able to abort a damaged collision quickly, so as it wouldn't damage a lot of airtime. Oh, and back off, which was intended to maintain stability on the channel, so that under heavy loading it would not crash in a bunch of retransmissions. Those are the key ideas that differentiated Ethernet from Aloha network, and which persist today.
What we mostly did in the product version was widen all the fields. The preamble went from 1 bit to 64 bits. The addresses went from 8 bits to 48 bits. The type field went from 8 bits to 16 bits. That was probably a mistake. It probably should have been 32. That would have made the header 16 bytes, which would have made lots of numerology nice. The CRC went from 16 to 32. Actually, the CRC went from 0 to 16 to 32. The original Ethernet, as we built it, did not have a CRC on it, and I kept telling Bob that was a bad idea, and he basically said, if you can find somewhere on the board, which was completely full, to put a CRC, then go ahead and do it. And so there was some blank space along the edge of the board, and I managed to drill some holes in there and press some IC pins in and get 2 more rows of 5 chips each along the side of the board, one for the transmitter CRC and one for the receiver. Then you had to be a little careful because we had metal card guides, and the pins were rather close to the metal card guides, and sometimes they'd short out. But I managed to get a 16-bit CRC in there. It was Digital Equipment, I think, who insisted that it go to 32 bits, and that was okay with me.
The standardization effort. I don't think we're really going to be able to do this, guys. But anyway, the standardization effort began in 1979. I left Xerox, left Ron, and well, all 3 of you were still there. And 3Com Corporation hadn't been found. What's that? No, this is when I went to be a consultant. And my first consulting client was DEC, and I had an agreement with DEC that I could consult with them on anything except Ethernet. And because that would be a violation of something, proprietariness or something. Anyway, Gordon Bell and I had a meeting, and he asked for assistance in as I recall, in helping to engineer a local area network like Ethernet, which was peachy keen, but which would not violate the Ethernet patent which Xerox had. And it was in that meeting that we had together had the idea, well, wait a minute, why don't we just write a letter to Xerox and ask that maybe we could cooperate or something. And so I drafted a letter. Gordon then completely rewrote it. And then we sent it to, he didn't completely rewrite it, but you put in the part about Xerox copiers and laser printers, which I viewed as a distraction. But anyway, we said, Xerox, why don't DEC and Xerox work together on developing an Ethernet that both companies could use to interconnect their products? And Xerox said yes. And then to make a long story short, in March of that year, I happened to be visiting the National Bureau of Standards, and the day before, a guy from Intel had been there with a new 25 megahertz technology, and he was there looking for chip technology for some applications for this chip. And I got his name, and I called him up at Intel, and one thing led to another, so that by June of 1979, DEC, Intel, and Xerox had agreed to work together to make Ethernet a standard. And one of the complications in that year was antitrust. The Democrats were still in power at that time, and the Democrats didn't like antitrust. So in order to get DEC, Intel, didn't like trusts. I'm sorry, I always get that mixed up. Who can tell anymore? And so DEC, Intel, and Xerox couldn't have a meeting until they figured out how not to violate the antitrust laws, and I got some legal advice from Howard Charney on how to do that. And in order to meet, they had to promise that the output of the meeting, they had two promises. The output of the meeting had to go to a standards body, ultimately the IEEE, and the second requirement is no marketing people were allowed to attend the meeting. The rationale being that marketing people might discuss prices or might discuss allocation of territories or something which, as we all know, are in violation of law. And that began a process that led to the creation of Project 802.3 in the IEEE, and then to an ugly, prolonged battle over standardization that lasted until December of 1982. And there were two major phases there. One was getting the IEEE. IBM came in and said, no, you can't make Ethernet a standard because token passing is better, and we're going to announce a product real soon about that, and so you better not make Ethernet a standard, the bastards. And so then it took a long time to get the IEEE to... There was this big day when the IEEE made a courageous decision, which was instead of choosing one of three standards, the Ethernet standard, the token ring standard, or the token bus standard, which had been kicked into the system by General Motors, and the IEEE made the courageous decision to standardize all three of them. And then it took a few more months for all the Ethernet people to stop wrangling with each other. So in December of 1982 is when the 19 companies in the 802.3 committee finally agreed approximately to adopt what DEC, Intel, and Xerox had proposed in September of 1980.
That chip that Intel was waving around with the 25 megahertz technology turned into the infamous 82586, if you know what that was. They were, I think, building a sort of a universal communications chip, and it already did synchronous and asynchronous and HDLC and bisync, and they heard about this thing called Ethernet, and they said, well, we'll throw that in too. Yeah, that's all I want.
I was going to add a couple thoughts on the standardization process. I think, Bob, you and maybe all four of us, I don't know, I certainly have the misfortune of having been at the founding meeting of the IEEE 802 committee at the Jack Tar Hotel. Were you there, David? Yeah. The Jack Tar Hotel in San Francisco when it had its old paint job. After it was part of an IEEE CompCon. And as I said, I'm embarrassed to have been there in retrospect. And there are a couple things that I can't quite get the timing done. But Bob, you and I had been traveling around the world giving local network talks. We had a 2-day seminar that McGraw-Hill had put together, and we would lecture and tell everybody all about local networks and mostly about the Ethernet, but we'd talk about other stuff as well. And all I remember is at this meeting there was this one guy who I won't name, who sort of was a complete know-it-all and who ended up in charge of one of the most important groups. And I kept staring at this guy and say, how do I know this guy? How do I know this guy who seems to know so much and is full of so much BS? And I finally realized that everything he knew about local networks, you and I had taught him a month before. And I said, we are in trouble here. Do you recall this guy? You don't?
I know.
And we sort of look, and this whole process in retrospect, I mean, if we had it to do over again. Yeah. You know, and clearly what we've seen in retrospect, you know, and if we had the right sense at the time, we would have just gone. I mean, you know, I've always said TI never standardized the 7400 family of logic. I mean, they just did it, and everybody looked at the book and they said, "Oh, I understand it, so that's what we'll do." And I think if I had it to do over again, I would have resisted this process. And instead, you know, we got sucked into this incredible political battle, and that didn't have a lot to do with technical merit. But you disagree? And let me just add one more story that comes a little later in the process. And I don't know if anybody else was at this meeting. We were out flogging I guess the standardization had happened, or we were still in the standards fight, but we had announced the Ethernet. And DEC and Intel and Xerox, particularly DEC and Xerox, were making hay out of this. And we were building this sort of fence around IBM, and IBM was struggling, trying to figure out what to do. And we were working with a bunch of companies, and our CEO gets a call from one of his colleagues at IBM that says, "I understand that, you know, you Xerox are really pushing the Ethernet, and you're working with computer companies, and would you be willing to talk to us about the Ethernet? We'd like to learn some more. We don't want anything secret, but we'd like to learn more about the Ethernet." And we said, "Sure, we're happy to do that." And I got the call, you know, "John, there's going to be this delegation from, you know, set this up with these guys from IBM." And David Liddell and I at the time were then in the Office Systems, I don't know what its name was, OSBU or something at the time. And so we had the assignment that this group was going to come from IBM, and they're going to come talk to you, and they want to learn a little more about the Ethernet. And we sort of knew they were the competition and so on. We knew a little bit about the token ring stuff. Were you in the meeting with us, Dave? And so you can correct me if I'm wildly wrong on this. And so there were 3 or 4 of us, and maybe 8 or 9 or 10 people from IBM, as only IBM could do. And some very smart people, guys that we knew who were good people. Paul Green from corporate, Lynn West, who had done a lot of network modeling, a couple of the guys from Zurich. And they came in and started throwing questions at us about, you know, well, can Ethernet do this, and how does it work, and what about this? And they had sort of a spokesman who was all lined up, and, you know, well, if we want to do this, can the Ethernet do that? I said, "Oh, yeah, no problem. Here's how it works. That works." "Well, what if you have this constraint?" "We'll do that." "Oh, yeah, no problem. That'll work well." "What if you have this other constraint?" "We'll do that." "Oh, yeah, we're pretty sure we can do that." "And what about this other constraint?" "Well, probably do that. You might want to do this little experiment and so on. But what if you had this constraint and this constraint and this constraint and this constraint and this constraint? Can it do that?" And there's a point at which we finally said, "Nope, you got us. You know, but by the way, you know, why do you want such a design? This configuration, this set of constraints is really crazy. This won't work." At which point one guy nudges the other guy and says, "See, I told you your design was terrible." And we find, and it had to do with, in retrospect, you know, what I think we finally inferred is, you know, what they were using, what the token ring guys were using as the stalking horse was trying to have something that would retrofit for 3270 terminals that were polled, and that, you know, and that's where all this deterministic latency and bounded access times, and you can put a whole new outboard box on, but you can't put any buffer in, and you can put a processor in, but you can't put any memory, and you got to grab these really small 2-byte packets under really tight time constraints, and can the Ethernet do that? And we finally said, "Nope, can't do that." And they went off and continued to do the token ring. Is this a reasonable approximation, only slightly embellished?
I think there was also some sort of civil war going on.
Yeah.
amongst the various
Absolutely. Yeah, there was clearly a war within the group as to what direction they wanted to go in.
At about this time, I got a phone. I was still working at Xerox PARC, and these guys were off trying to productize it and sell it to the world. I got a phone call from a headhunter, and he offered me a job in upstate New York, leading a group of initially 20 researchers working on local area networks. I get to sort of pick the theme and lead it, and of course, if it works, then I'll be a section chief and have 40 people within a year or two and lots of money. And how does this sound? And I was just totally uninterested. I was having a ball at Xerox, and I wasn't interested. He kept dropping more and more enticements, trying to get me interested, and I was just not interested at all. I finally caved in and said, "Look, the vice president of R&D at IBM, was that Branscombe or?" "Yes." Basically tasked me to call you and try to recruit you. "We want you to come to IBM and set up a lab and do Ethernet." And this must have been happening at exactly the same time. It sounds like it.
Should have called me. So the standard ultimately got made, IEEE. It was first made a standard by the European Computer Manufacturers Association while the IEEE thing dragged on. Then the IEEE got embarrassed by the fact that Europe was out ahead, and so they made Ethernet a standard, and then it was ultimately made an ISO standard in 1990, I think it became an ISO standard. February of 90, I think it was made an ISO standard. Now on to the hot product, which is basically, yes, sir.
Is Ethernet the last technology for which any significant engineering was done before the Standards Committee got their hands on it?
No, the last one. IEEE 48 was done this way. That is HP. That was before. That was our model, in fact.
We use that as our model.
And then the...
They stuck under the wire. You didn't quite make it.
yeah, I see. I gather that was sort of a compliment. Yeah. Yeah, I disagree with John. I think that the over-engineering and the delay and all that stuff was worth it. And that the making of Ethernet of a standard was critical to its success in the marketplace, despite the inefficiencies of time and over-engineering. And I think that I would do it again, as painful and ridiculous as it was. Yes?
How did you manage to resist Xerox's impulse, which would have been to patent this and hold on to the technology? This was IBM was patenting book.
Xerox did patent it, and there are Xerox patents. And in '79, DEC and Intel and me persuaded Xerox to put those patents into the public domain for purposes of creating an industry standard. And that was a very hard thing to do because Xerox was built on patents. It was built on the patents for the copier. But the rationale was that the purpose of networks is to connect things, and it doesn't make any sense for you to have the only ones. You know, you need to have other people have them so you can connect to them. That was the rationale. And to the credit of Xerox management, they got that right away, and off it went.
Actually, I have the memo I wrote in response to your proposals. There was a review internally of what to do about this proposal from Bob and others. And we went through some of the examples, and one of the most well-known ones at the time was DataPoint had the ARC network, which they didn't want to call a local network, and which was completely proprietary, and they were insisting that this was better than anything else, and this was going to differentiate their product line, and it was going to help DataPoint succeed in the computer business. And I wrote this memo that said I thought that was a terrible idea, and that DataPoint had exactly the wrong strategy on trying to differentiate their products based on their communication strategy, and that we ought not to go that way, and we could outflank them by going along with this proposal, which has sort of been instituted from the outside, to go ahead and license the patents.
So three of the major adversaries of Ethernet were IBM, DataPoint, and Wang, and you've seen what happened to those companies as a result.
A comment on the standards effort at Xerox. They did use the patent to help guide and direct the standards effort by licensing the technology relatively cheaply, like $1,000 for a lifetime paid-up set of Ethernet addresses and a license to manufacture and sell product in that area. But basically, you wound up conforming to the spec, and that was very useful rather than having people go out and build multiple different types of implementations of that. And the IEEE standard that came out was substantially the same as the Ethernet spec as released in September of 1980. That is, equipment would interoperate on the coax cable exactly. The tolerances in the IEEE spec were made somewhat tighter, but the actual center values for the voltages and whatnot were the same. Question? Why are the packet formats different? The primary difference is the type field, which is there's a destination address, a source address, and then a type field in the Ethernet. And in 802, they made that a length field, and then they had a DSAP and SSAP stuff that occurred after that. And that basically caused that's a source of incompatibility. personally, I believe the type field is the correct thing to include in the format somewhere, because that allows you to demultiplex multiple protocols at the next higher level. You don't have to freeze everything. You can select protocols with a 16-bit field. You can look at the protocols and demultiplex today's protocols, and you could assign a number to the utopian protocol of the future. You could call it the ISO protocol, for example. And then when it finally becomes available, you can use it, but you can continue to sell equipment and build product today. And as time goes on, if there is a new protocol, you can migrate to it, rather than having to throw away everything or undo your system to bring in a new protocol.
I think it was a religious war, and this is where I differ a little bit, but I think it was a religious war, and it was used as a mechanism to slow down the standardization process as we fought for 6 months over this one lousy field, whether it was going to be a type field or a length field. Oh, I don't know. Yeah, I mean, somebody walked in and said we need a length field, and we kept saying, why do you need a length field? Because, by the way,
I feel good knowing how long this packet is.
Right.
And we said, but the hardware will tell you. You know, you can read the entrals of the DMA transfer or whatever, and tell how many physical bytes or whatever were transferred, and then you can look inside the packet once you know what kind it is by looking at the type field and figure out how long it thinks it ought to be, and then if physical doesn't match logical, throw it away. And they said, no, and it was religious.
They said, well, you need the length field in order to verify that the length is correct.
Right.
Which we said, excuse me, the CRC will be blown by the time that happens. So it's not giving you any extra information. But it just became, the technical arguments, I would assert, were tools in a business and marketing
Who had
battle.
the inspired idea of making the compromise where the length became the low values of type? Who did that?
I don't know, and is Bob Prentice here? Yeah. Yeah. I mean, you could therefore make it interoperate with sort of the slightly artificial kludge that you had to require that all the type fields had the high order bit 1, and you knew that the length would never be that big, and therefore you could intermix these two things, but you then had to sort of look and test the bit to figure out which the hell thing you got, which was really dull. But do you recall, Dave, where that came? Does anybody recall where it came from? I don't know. And that's how we finally cut the Gordian knot.
Speaking a little before about Xerox holding things proprietary, the CACM paper on the Ethernet was held up for at least 6 months before Xerox decided. I guess it was held up until the patent was filed. That's really what happened. The manuscript was at the CACM. It had been refereed. It had been approved for publication. It was ready to go, and Xerox wouldn't release it for publication until the patent had been filed and all the legal things had been met. And then there's rules about you can't publish for you probably know what they are.
It had also been widely distributed at DEC before publication too. I think the referees worked at DEC, and I'm sorry, I didn't mean to mention that.
That's right.
I guess I'll talk a little bit about where the productization of Ethernet. In the first stages at Xerox, we worked on what was called Xerox Wire, and that ultimately resulted in presentations that we did to Digital Equipment Corporation and Intel in May and July of 1979, which resulted in the companies working together. And that effort took until September 1980 to actually produce a standard that was published as the version 1 Ethernet standard. In that time period, we started evaluating implementations, because the standard, of course, had to be implemented and be workable. So we built prototypes of transceivers. Some people at DEC, whose responsibility was the key transmission system issues, they looked at some of the coax cable, and with respect to some of the over-engineering in retrospect, the moving from a single shield braid shield coax to a coax that had 2 foil shields and 2 braid shields and cost $1 a foot was certainly an effort. It was very good coax, but it was much in excess of what was necessary. And the key testimony to that is ultimately we built a system using what's called thin coax cable, or RG58 cable, which was a single braid cable, whose impedance was even higher, or whose shielding transfer impedance was even higher than the single braid thick cable. And we never picked up much noise in that in the building, so clearly there wasn't much risk of the fat cable picking up much. In doing the transceivers, people were very concerned about redundancy. So this was an early version of the PC board that went into ultimately this early DEC transceiver, and there was several sections of the circuit were triple redundant, which is kind of expensive when you're building it out of discrete components. At 3Com, our first product there was a hardware product, was a coax transceiver, which is this box here, sometimes called the brick, because if you weigh it, it's about 28 ounces. It has a pound of potting material in it, which actually went in for 3 reasons. One of them was mechanical rigidity to provide solid support for everything. The second was thermal conductivity to conduct heat out. And the third was to basically make it so people couldn't see what was in it. And we yes?
Justify its high price.
Oh, yes. Well, that was part of the third reason. If people could see inside, they said, "Well, transistor radios look like this." Namely, a board with a bunch of parts on it, and there's about 200 parts on the board. A number of the resistors were sitting on end, just like in the transistor radios from Japan. That allowed higher packing density, but the manufacturing people had a less than wonderful view of that here, even though it seemed to be standard practice for the cheap radios you buy in drugstores. This transceiver was built first in a stamped and drawn aluminum box. Then we went to a stamped and welded box. Then we went to lower cost things. All of these transceivers, by the way, have 2 interfaces. An interface to the transceiver cable, which went to a controller, and an interface to the coax cable. Either it was a through connection or it was a tap connection, as in these. And the actual connections is just a connection to the center conductor and the shield of the cable. Question?
Who's responsible for the sliding connectors?
The slide lock. The propagation of that, I used what was on the Alto transceivers, and I'll let Dave answer why it was there.
The person you want to blame is named Charles P. Thacker. He's a senior corporate consulting engineer at Digital Equipment now, I think, something like that. He's the principal designer of the Alto, and as the designer of the Alto, he picked all the connectors and hardware on the back of the Alto, and he used slide locks everywhere. And by the time we got to it, the only thing he'd actually used all the sizes. He used the 15-pin one on the display, and the 25-pin one was something else, and the 37-pin one was the keyboard. And we weren't left with much, so I guess we used a 15-pin one, and we arranged our pins so that if it got plugged into the display, it wouldn't matter. But all of them used slide locks, and so we used slide locks, and so it was Thacker who started it. I heard the Stanford linear accelerator people used to hate the slide locks. The first thing they'd do with all Ethernet equipment was take it off and put screw locks on. I guess it could be inconvenient if one of them fell apart in your accelerator somewhere. But they used to strap the coax. I was at Lawrence Berkeley Labs, and somebody showed me with delight how the beam line was coming down the hill from some big accelerator up the hill, going to some other accelerator down the hill. And tie wrapped to the side of this giant high vacuum pipe with plasma running through it was my coax. And it had no problem being right next to the beam line.
The problem that occurred with the slide locks was that there's a locking pin that hooks onto a post, and the post is mounted about 30 mils off of or 1/16 of an inch off of the panel. The sliding mechanism itself was typically flush against the connector, and that worked fine when the slide latch was on the cable connector, and the posts were sticking out of the panel because the 16th inch offset for the post would allow for up to 1/16 inch of panel thickness. You had little spacing washers that you would either insert or not insert depending on the panel thickness. The problem arose on the controller end when we built for the controllers. In doing the cables for the Ethernet, I chose to make the cable also be an extension cord for itself, which is to say one end had a slide lock and the other end had the post. That posed a problem for the controller because that meant it had to have a slide latch. Many companies, when they implemented that, did not pay attention to the fact that the slide latch had to be mounted flush to the connector, and they would stick it on the other side of a 1/16 inch, and in fact, in some cases I saw on the front side of a 1/8 inch thick panel. There's a problem. The overlap of the pins was only 1/8 of an inch. So if you pushed the thing out 1/8 of an inch, the end of the pin could just barely touch the end of the barrel it was supposed to push into. And this, of course, resulted in pretty unreliable connections. And sometimes you would see people with the cables tied in knots trying to bend the connector into some position where in fact it might work. And in fact, the real problem in most of those cases was just that the original design of the equipment didn't take into account the actual connector dimensions. Mark?
Would you like to comment on Crinsley's account of the transceiver design?
On
Robert S. Crinsley and Accidental Empire? I've read it.
Oh.
Well, I've read the book, but I don't remember.
What was the...
From a few bars, and I'll see.
Pardon? Was this the account of the acoustic problems? Or?
But I'm trying to get Ron to talk about his baby, the Etherlink, of which probably 6 million have now been made in various forms. But he keeps wanting to talk about the goddamn slide locks, which is underscores the story that you read in Accidental Empire. Now, Ron, would you just talk about the Etherlink and get on?
Okay. This card was... This was the first product. It was fairly high volume at 3Com. It was an Ethernet adapter for the IBM PC. And it consisted of discrete logic for virtually everything except for the Ethernet controller, which we got from a company called Seek. It was a startup company at the time, and in fact, the first time we talked to them, we were looking to see if we could do a gate array. We had done some estimates of how many ICs it would take to actually build a controller on a 52 square inch board, and it appeared that we could fit one on with discrete parts, but no transceiver. And I was exploring gate array technology when this company visited us, Seek Technology, and they were talking about building an Ethernet controller IC chip, which we thought was all very interesting, but it seemed that they didn't really know that much about this stuff, so we weren't quite sure what to make of this. And about a month later, they came back and visited us again. They seemed to have made considerable progress in that month. Apparently, they had an effort underway, and they seemed to be very knowledgeable about what was going on and expected they would be able to produce silicon in some number of months. So we immediately abandoned any effort to find a gate array manufacturer and decided to work with these guys because that looked like the best path to having a controller. So we focused on building the bus interface, providing some advice to them on making sure that we had the correct functionality in the part. The part itself basically took the serial data in and out and converted it into byte-wide data. It did the CRC calculations on both transmit and receive. It had FIFO buffering, and it did the binary exponential backoff algorithm. On the board, pardon? Yes, it did address recognition as well. On the board itself, we had the buffer management that took the data from the FIFO, put it into a single 2K by 8 buffer, and we had a bus interface that allowed the data to be taken out of the PC bus or written in from that port. Yes, question?
Can you elaborate on an earlier comment that was made that you would never design another half-duplex controller again?
That was me.
Is that,
Yes.
true of those?
These were in effect. The actual design of the controller was full duplex, but when we got to the buffer management, it became half duplex. Although this thing actually will perform loopback. It actually can operate in a quasi full duplex mode relative to the network. It cannot, it can't define or delineate packet boundaries. So if we were to allow packets to come in on top of each other without emptying the buffer, there was no mechanism in this particular board to identify where the end of the packet was or to store the status associated with it. You had to read the controller buffer directly for each packet. The analog electronics on here was, there's two pieces. One is the encoder-decoder, which is a Manchester encoder-decoder. And that was made out of ECL logic, and there was a transceiver, which we did, and it was unique in that it had, it has no DC to DC converter. The ground isolation was done right at the signal connection to the coax by using very well balanced transformers and a two transformer output stage that allowed a flyback time for the diode coupling. So we were actually able to have a direct connection and detect DC levels on the cable, although we did not actually have a direct any circuitry on the coax side except for a couple of resistors and diodes.
This was a really
So
good
that's
product because it avoided the transceiver, which cost a couple
Right.
$100, and the transceiver cable, which cost
Yes.
a lot too.
Actually, at that point in time, the transceiver cables were selling for $100 to $200.
Yeah.
They were very much overpriced, but people paid it. The connections to the outside world were the thin coax, which was through a BNC connector, and we retained the thick coax, the regular transceiver cable connection, because at the time we did this, it was a new idea. We weren't sure if the thin coax, as it goes around to each workstation, whether people would randomly just pull the cable off the back of their machine and open it up, and thus bringing the network down, because it was now in the user's hands, as opposed to the end of a transceiver cable, which could be detached and have no effect on the network operation. Turned out that it worked out quite well, but when we did this, we didn't know. Another thing the AUI connection has provided over the years is the ability to migrate to other media, that is, other than coax. For example, fiber optics, or point-to-point microwave links, or broadband transceivers, which have been used, have found limited usage in some campuses. This board, we took the technology of this board and moved with the use of a gate array and a integrated encoder-decoder, and moved to a two-layer board, which has fewer parts on it. Still has the discrete transceiver. And then several years later, we went to this board where we got the gate array. This large piece here was repackaged, same die, but in a different package, PLCC package. And we got an integrated transceiver chip. And that resulted in a small board. And there's quite a few of these boards were shipped. I think 3Com is now shipping stuff. It's a board about this size, but has about one chip in the middle, and it's a two-layer board.
And you can now buy 10 packs of Ethernet controllers at Fry's for $99 each. 10 packs for 99 bucks. We dreamed about that at the time. Actually, yeah, I think it's from SMS. Yeah, right. SMC, whatever.
These boards initially in 1982 sold for $950 a piece. These were $950 in 1982. Yes, that was, prior to that we had, this is, I think it is.
That's a 3 megabit unibus.
This is a 3 megabit unibus. There's also, 3Com also had a unibus controller that was a hex-wide controller, and that sold for several $1,000s.
However, the
Yes.
Xerox 820 10 megabit controller was retail $600 at the same time.
Yes, the
Our
Xerox.
goal was about $500 for a host interface. The computers cost about $25,000 to $30,000 each few percent of that, 500, less than $1,000 certainly.
I used the 820 price as an insistence proof several years trying to argue, why are these guys charging $2,300 for these Ethernet transceivers?
All the traffic will bear.
Yes, in the back.
I'm really curious about one thing. I was wondering, in the course of your travels, how many companies you run into that have run afoul of the whole unique addressing mass production conflict, and who the most egregious offender was? By my life, it's AT&T with 3B2, but I'm just wondering how many other companies out there were really good at making lots of things, but not really good at making lots of things, each a little bit different.
The question has to do with the mass production of equipment which has Ethernet addresses, each board having a unique address. I'm not aware of too many. I'm sure the problems have cropped up. I know at 3Com Corporation we once had a problem where someone asked me, I guess they had just made a change some afternoon, and one of the technicians asked me when I was coming back from dinner, he says, why don't you come over here and tell me about this. He says, see the address problem? Well, here's the number in it, and they tell us that it's okay to have the number written on it be different than the number that's in it. And he thought this was a problem. And I certainly did as well, but apparently somehow it had gotten past someone because they believed there was, there was some other production issue that made that okay. We stopped shipment of everything almost immediately, and the next day people sorted out what they needed to do, and of course it got fixed. I don't think much of that ever got shipped. It was whatever went out over, I think, over an afternoon or something. But that was an issue. That was a very serious issue. We tried to watch after that very carefully.
How many machines did AT&T ship with the same serial number?
They still are. I had 3D2, and I was part of a crew in putting 3D2 in every Navy base in the world. When you buy a 3D2, out of the box, they are all the same, and they give you a Xerox piece of paper telling you what you need to do to set it and what range and how it needs to be set, like with what it needs to be loaded. It's ridiculous.
I didn't know that.
I must not be in a wrong.
News to me, but
Over the years in building these, as I was noting, the transceivers they have two key interfaces, the AUI interface and the coax. And you saw you would get big ones. We had little ones, internal boards. There's long ones. They come like this. We started out this way when we got an IC chip, but we weren't sure whether we were going to get it. So I had the case made long so we could put discrete circuits if we needed. This box is largely empty because we were lucky. The IC chip came in and we never had to do the discrete one. This is how big it was with a discrete component. This thing, at least those of you who are taxpayers might be interested, this thing was made for the military by a company who OEM'd the board that was in this, put military mil-spec components in it. We designed it so it would work over the military temperature range. Put mil-spec components in it, put it in this milled out block, and took this, which used to sell, we sold I think initially for $295 list price, and kicked it up to $6,000. I don't know how many they sold, but you don't have to sell many to make to make it a worthwhile investment to buy the milling machine or hire somebody to mill it out. As ICs proliferated, the boxes got smaller. With this amp tap, we had a standardized interface, so the tap could plug into a number of transceiver types. IC companies started almost giving away these things as a demo board to convince other companies to build the product. The Japanese got in, and they made an even smaller transceiver. Again, you have the AUI interface, and this is where the coax cable goes for the tap. I think I've covered about all of the stuff here. Around '87, we started looking at twisted pair stuff. This was a pair tamer, or a module that converted the coax signal into an unshielded twisted pair for telephone wire, which was done at 3Com.
Ron was the guy who started Twisted Pair Ethernet.
That's, well, for the single pair stuff, yes. There's also two pair stuff, which ultimately became the standard. More people knew how to do that because you had to transmit on one wire and receive on the other wire, which was easier to do. It was a modification of what the AUI or the transceiver cable, they also called AUI cable. The interface here was, the transceiver is also called a media access unit, and thus the interface, the transceiver cable that went from the transceiver to the controller was called the AUI cable, or access unit interface cable. And that cable, by the way, has 3 signals in it: transmit, receive, and collision detect. Question?
Transceivers. Do you remember what impact the lightning strike had on transceiver design?
What impact lightning strikes had on transceivers? This was an event, I guess, in 1978 at Xerox. There was a lightning storm. We had, on the campus, we had several buildings across the street from each other on the top of Coyote Hill Road. And it appeared that there must have been a large shift in the ground reference voltage in one building relative to the other building. And the Ethernet didn't work one morning when we came in. And so people went down and they found a transceiver, tried swapping it out, and that didn't work. And they continually tried this, and it continually wasn't solving the problem. And it was a new kind of problem for the technicians, because they had always made the single fault assumption. That is, one thing's bad, like a Christmas tree where you had all of the bulbs in series. If you assume only one bulb is out, you just go down the line and try swapping it with a known good bulb until you get to the end of the line and it will work. But what if 2 bulbs are out? Then then that algorithm does not work. And that, in fact, was the problem. They had blown out about 25 transceivers on this net because a large potential difference occurred between the center conductor and the shield. And on the early alto transceivers, the center conductor and shield, the receiver input transistor had a collector base junction sitting directly across it, which, when biased in one direction, there was no problem at all. And in the other direction, you basically blew out the junction if you put more than about 0.8 of a volt on it. And a lot more than 0.8 of a volt appeared on these. There wasn't any series resistor to limit the current on the base input of the transistors.
The next batch.
Yes, the next batch had that. And as did all of those which had been burnt out, and we had to put a new transistor into it. But that was a lesson we learned in terms of making sure that the input circuits could tolerate a reasonable voltage, both positive and negative, between the center conductor and shield of the cable. The method we finally used for diagnosing the problem was to use a TDR. Basically, we got a pulse generator and sent a pulse into the cable, and I could see how far down the problem was, so I'd tell somebody, okay, get something at this distance, and they'd pull it off, and then I could see the next one. So they just continually pulled off transceivers until all of those shorting the cable were removed. And then we had a working system again. And all we had to do was fix all of them.
Okay, so we've talked about the invention of the technology, the invention of the standard, and the invention of the hot product. And it's really kind of late. What should we do now? David wants to talk about the future.
Well, just a little bit. I guess you've all heard about fast Ethernet. Once again, actually, it's Ron Crane there who had the breakthrough idea. Ron and Howard Charney and I and gosh, who else was there? Larry Birnbaum? Yeah, he was there. Well, anyway, we were kicking around ideas trying to decide what we could do to make some money. And I was actually proposing building an Ethernet diagnostic box. Actually two things: a little handheld unit you could plug into an Ethernet port, and it would sort of light up red or green and tell you whether the thing worked or not. And then maybe a larger unit that would measure parameters on your network and give you a little health indication. And that had some promise, and we followed that up for a while. But Ron then quietly mentioned that we could make Ethernet go faster. We'd been talking at the time and looking at Crescendo Communications, who had been doing 100 megabit FDDI over copper wire, and we've been talking about how people don't actually use the Ethernet the way we originally designed it. We envisioned stringing a long piece of coax down the hallway and tapping little transceiver boxes into it, and each individual computer had its own transceiver, but that's not the way the world is wired. The way the world is wired for Ethernet is home runs from your office to no more than about 90 meters to a wiring center where there's a hub of some sort. And Ron pointed out that if you cut the collision, the electrical distance over which collisions have to be resolved by a factor of 10, then you can speed it up by a factor of 10 in bit rate, and everything cancels out and it still works. And wouldn't that be an interesting idea? You don't change the software, you just design something that's 10 times faster. And Ron is working on that, and it's moving its way through the IEEE Standards Committee, and there are a couple of startup companies who are designing products for it. I think they'll be out. They'll be probably showing them at the next trade show, if I had to guess. And this is this is giving heartburn to FDDI. I've heard rumors about canceled FDDI chip projects because the business managers said we're never going to make our money off of it. Fast Ethernet is going to keep FDDI off the desktop. Fast Ethernet may also take some of the market away from ATM to the desktop. Although both of those technologies have their place, it's not clear they have a place on the desktop. Bob, I should point out, Bob's on the board of directors of one of these. You're not? You're not anymore? You were?
I'm a publisher.
Oh, okay. You have to be public about this? Okay. Well, anyway, 100 megabit Ethernet is going to hit the market this year, and it's been working its way through the IEEE standards bodies. Ron goes to all the meetings. I read the Communications Week magazine, so he's the expert. But my reading is that a breakthrough event happened a couple of weeks ago in the IEEE, whereby a distracting proposal from Hewlett-Packard got moved off into a separate study group, leaving the field pretty much free to the pure Ethernet versions of the 100 megabit fast Ethernet proposals. And I think things are going to move along pretty fast now, and you'll see product pretty soon.
You see anybody in the 100 megabit standard modifying the back-off algorithm to solve the capture effect?
No, there is no, right now, no proposal for modifying the back-off algorithm. I expect, although there has been little discussion of it to this point, that we might do something if the effect that's being referred to here is a capture effect. If you have one or two stations that are transmitting at an extremely high rate, pretty much at the minimum inter-packet gap, it makes it difficult for another station to get in. In fact, if the other station tries and it gets a collision, then the other station winds up waiting for a while, and the first station transmits its packet. So ultimately, when the next opportunity comes up, the other station is on its first transmission attempt, and the second station, the guy who had to back off, is on his second or third one, and he has a high probability, certainty of having another collision, at which point he gets backed off even further. So that's the station that's, once he gets started on the back off, he winds up potentially seeing a relatively low data rate. This relates to the fairness issue, and there are things that can be done to the spacing of the inter-packet gap, how much of the back-off time you allow the transmitter to be reset by the presence of another signal, and the point at which you make an irrevocable decision to start transmitting. So there's sensitivity. It all occurs if the transmitters are really closing down. For example, on a 10 megabit system, when you run the interpacket gaps down from roughly 12 to 9.6 microseconds, when you start squeezing it into that range, you start to see some of this effect. Most of the controllers they're presently out there, you don't see this effect either because the software won't do that or because different controllers have slightly different minimum interpacket gaps. Yes?
We now know of 3 different major computer vendors, one of which at least uses the SEEK part and others of which use different parts, that are seeing that as a very serious problem because current RISC machines can just saturate.
Yeah. Yes, that is.
And I have, after the meeting, I don't want to distract, I have some handouts if anybody wants to talk about the part.
Sure.
That's sort of
Great.
a soft spot in the original
That-
Ethernet design.
that-
You don't get that interpacket gap right at the end of one packet,
It has
at the
nothing to
beginning
do
of
with the
the right.
interpacket gap.
No, but there's some other issues that can be dealt. I mean, there's an issue that when
It
this.
has to do with the rule for when the access negotiation is over. Is it over when I win, or is it over when somebody wins?
Yes, that's right.
That's it.
And that's an issue I think has not been discussed widely at the standards meeting yet. I expect that is an issue that people will deal with. It will be using a higher speed transmission medium to some extent relieves us of some of that only because you have adequate bandwidth.
No,
But
at least one vendor that can saturate an NVDI.
That's true. But the question, I mean, but if you're that's right. I mean, if you're actually saturating the network, then you're really just using the thing as a point-to-point link. And
If you really have an application that requires, on a sustained basis, 100 megabits point-to-point, that's what God invented point-to-point interfaces for.
Strings
Right.
and coax.
It's not that issue when you run standard TCP with,
No, the point.
it happens.
The point that he's referring to occurs, but you have to be on a highly loaded network for that to occur. Yes, that's right, but they have to be trying to get
A sender and the guy who's trying to act sender will slow the throughput down to 800K. Offline.
Yes. I mean, there's other ways to solve that problem. It's not an unsolvable problem. Yes.
2 quick questions. One, what is the median for 100 megabit Ethernet, and are the packet formats the same?
The media is everything in the packet formats are unchanged.
Yes, the goal is to try to run on initially on the twisted pair wiring, either the data grade or voice grade wire. We're trying to get stuff that would operate on voice grade wire. It's quite clear that the data grade wire solutions are available, can be used because you could obviously just use what FDDI committee is doing.
Will of course work
Yes.
on any filter environment.
Yes. Any?
Any at all.
Yes.
I mean, I've been trying to get a line on 100 megabit. That's the way to find it. I mean,
Read Communications Week newspaper and other maybe
There-
Info World newspaper.
There's an IEEE standards meeting on that sub. You can.
It's public. The IEEE is doing this out in the open. It's all available if you want to go.
The next IEEE meeting is in Denver. It's the week of July 12th. So
802 dot something else?
it's the 802 plenary, and it includes 802.1, 2, 3, 5, and all of the.
What is the 100 megabit dot?
That is .3. It is within that group, which is the one that provided the standard for Ethernet. Yes?
the fact that both IP and several other protocols are going through a problem of running out of addresses. Are we running out of addresses with that 48-bit station address?
Not that I know of.
I don't believe so, although they're divided up into 24-bit.
Until 1948, we didn't know what we were doing. Pretty much shattered public.
Another problem might be things broken.
Yeah.
If you have
It's been a steady improvement in IEEE transactions on communications. The coding just gets better and better.
stamping or if the cable's too long.
The first product was the transceiver. First,
Yeah, we have several channels of network audio.
Remember?
and then
78, that one Oh, okay, you work for him? Oh, okay. This is a Nova.
Your company's working on 100 megabytes?
His own personal photographer. I'm impressed.
I'm trying to follow the 100 megabytes market.
David Cashton was at SRI and
We stepped above the
make
I'm with